The instruction set architecture, also known as ISA, specifies the format of its instructions and then primitive operations that machine can perform. So the ISA instruction set architecture is an interface between hardware and software. So that's the very bottom layer the programmers can see is an instruction set architecture. Some CPUs or computers has hundreds of different instructions, but Maria uses only 13 instructions. Actually, it is a 4-bit OP code, which means 16 instructions are possible, but out of 16, only 13 are being used. So here is the instruction format. Out of 16-bit, we use the upper 4 bits for operation code. So we have a 13 operation code, and then the remaining 12 bits are for address. When this RP code, operation code, needs some memory location, that memory location is specified in this field. So here are first 9 instructions. So 0001 in OP code means load X. Load X means load the contents of address X into accumulator. So here in this 12 bits, an address is specified. Then if OP code is 0001 and then some address, then what it does is that from this location, whatever the address is, it reads data and store that into accumulator. That's a load X operation. And then store X is the opposite of operation. So binary code 0010 is there, and then some address is specified for example, 10000011 and so on. Then whatever is currently on AC accumulator, that contents will be stored at address X. That's a store X operation. So next operation is 0011, which is add X. So whatever address is specified, what this operation does is that add the contents of at this address with the accumulator, and then the result is stored back to accumulator. So what it does is that accumulator is updated with accumulator plus in memory location whatever the X specifies. That's add X. And subtract X is very similar, but instead of addition, subtraction is performed. So as you can see, when you need two data in any of the instructions, the accumulator is one of the two data. The input and output is a very simple read from the keyboard or display onto show the value on the display. Always it's into accumulator or from the accumulator. That's input and output. Halt is to simply stop the program, which indicates the end of the program execution. And then we have some a little bit complex operations. So OP code is a 1000. Then it's a skip conditional instruction. Means that skip the next instruction based on the condition. Details of this one we will see on next slide. And then 1001 is a jump X. Jump X means the load the value of X into PC. So what it means is that PC is a address of the instruction to be executed next. So address of a next instruction is stored there. So as you load X into PC, the PC will become X, means that the X is the address of a next instruction to be executed. So effectively we can jump into some location. If I have a jump 1000, then next instruction to be executed will be read from address 1000. So that's effectively a jump X operation. So let's take a look at load instructions. In the previous slide, load the OP code is 0001. So here 0001 is OP code, and then whatever you give here is a address. So here address in decimal equivalent is a 3. So what happens is that the whatever value at memory address 3 will be stored into accumulator. That's a load instruction, and this is instructions instruction being executed that will be appear in IR, instruction register, actually. So based on the contents of the IR register, what it does is that from this location address 3, we read the data from the memory and then store into accumulator. That's a load instruction. And then skip context instruction is skipping the very following instruction. Is OP code is 1000, and then condition is specified within these two bits. Bit 11 and bit 10 is to place condition. So at this moment, so 10 is there. The meaning of 10 is the next instruction will be skipped if the value in accumulator is greater than 0. So this one specifies whether to skip next instruction or not based on the value of accumulator.